right, in this video we're going to look at the column space of each of these matrices and think about being able to describe that geometrically, and really the ultimate goal here is to be able to find a basis for the column space of each of these matrices. All right, so I'm going to start out by just using the definition of column space to write down the column space of each of these matrices, and then we'll dig into that and think about what it means for this particular matrix. All right, and I also chose matrices of a couple different dimensions just so we have a little bit of contrast in the examples we work with here. All right, so the definition of the column space, so the notation I'm going to use here for the column space of the matrix B, column space of B, this is just the definition of column space. It's the set of all linear combinations of the columns of the matrix. So here I have two columns. So the set of all linear combinations of 2, 5 and 4, -1. All right, so I'm going to write that down, the set of all. And then I'm just going to write down a generic linear combination of these two columns. So I'm just going to use A and B for the scalars here. So A times the column vector 2, 5 plus B times the column vector 4, -1, where A and B can be any real numbers. You maybe don't necessarily have to write this, but this part, maybe that's understood that A and B can be any real numbers. So I'm going to go ahead and write it though, but you could probably leave that off. So this is really what we're going to work with in a little bit and think about what does that actually describe and then find a basis for that space. I'm going to do just that much though for this example first, just so we can focus on understanding that definition. So set of all linear combinations of these columns. So I have 3 columns here. All right, so the set of all column space of the matrix C is, by definition, the set of all, I'm just going to use A, B, and C again here. So A times this first vector plus B times the next one Now for sure, if you've had linear algebra, you might notice some important things about these particular vectors on this one in particular, and you might be able to go leverage a lot of stuff you know from having a whole linear algebra course and go right to being able to write down a basis for this column space. So just understanding that you're using a lot of connections that maybe our students in our class haven't had yet. So we will get there at the end. But what we want to talk about is why is that what works. Okay, so definition of column space. You want to make sure that that is set in your mind when you think about column space. Set of all linear combinations of the column vectors from the original matrix. Okay, so I just wrote that down. And then the next thing that we're going to do is dig into that and think about what that might describe geometrically and think about a basis for that. All right, so there are a lot of ways you can do this. What I like to do is go ahead and do this scalar multiplication. So I would multiply the vector 2, 5 times the scalar A. So I'd have 2A and 5A. Same thing here. And then go ahead and do the matrix addition. So I'm just going to do that as all one step. So I'm going to do the scalar multiplication and addition here and go ahead and add those. So I'll have 2A plus 4B and 5A minus B. Now be a little careful with notation here. Notice that this is a matrix. The first entry is 2A plus 4B. That's all one entry. And then the second entry is 5A minus B. So this, while it is distracting maybe because of the way things line up when you write it, this is a 2-by-1 vector, right? First entry just has multiple terms in it. Right? And just thinking about that here, if I take a 2-by-1 vector and I add it to another 2-by-1 vector, I'm going to get a 2-by-1 vector. All right, so that is a 2-by-1 vector. So we are looking at vectors that are in R2, right? These have 2 entries, so this is in R2. So we might think about an XY coordinate system here. It's a geometric representation of R2. Another question might be, is it all of R2, or is it only specific vectors in R2? And there are a couple of ways to think about the answer to that. I'm going to go back for this one up here to the definition and think about these vectors, 2, 5, and 4, -1, that are in R2. And I'm going to just plot those two vectors here on my xy coordinate system. I'm not going to scale off the axes and make this perfect, just kind of a sketch of these two vectors. So over 2 and up 5. So we're going to have a vector here in quadrant 1. I'll call that one V1, the vector 2, 5. And then another vector for -1. So over 4 and down 1. So we'll be down here in quadrant 4. Oh, and I probably didn't draw these the right length, but that's okay here. What I'm really just doing is a simple sketch, not a perfect diagram of these vectors. All right. So I'm just thinking about the vectors I started with, and then I want to just leverage a little bit of geometry that you might know from when you first started working with vectors and doing vector addition and scalar multiplication and all that kind of stuff. So when I think about the vector 2, 5, I just drew that in standard position, tail at the origin here. And then when I take scalar multiples of that, I'm going to get all different lengths of vectors that are along that same vector and maybe in the opposite direction too if my scalar is negative. So taking scalar multiples of this vector 2, 5 is just going to give me basically everything along that vector 2, 5 in the xy plane. And then same thing with the vector 4, 1. When I take scalar multiples of that, I'll get everything this way. And then if you think about geometrically vector addition, if I take a vector and then I add it to another vector, you might remember drawing those little triangles really where you put the vectors head to tail and think about what you get when you add them. But essentially, if I take one vector and take scalar multiples of that, I'm going to get everything along that. And then when I take those scalar multiples of the other vector and add it, I'm going to get everything kind of parallel to that other vector. So eventually, if you think about visualizing that, I'm going to eventually get all of R2 by taking scalar multiples of these two vectors and adding them. I'll get every vector in R2. So what I've drawn here is not every vector in R2, but I used those to think about taking all scalar multiples and all vector sums of those resultant vectors. And when I take all linear combinations of that, I will eventually get all of the vectors in R2. So these are vectors in R2 because I know they have 2 entries, each of which can be a real number. The question is it all of R2 or maybe just part of R2? In this case, we actually end up with all of R2. Whoops, all of R2. Okay, so this column space happens to be all of R2. Not every column space will be, but this one is all of R2. You might remember back to the null space for this matrix, this same matrix. We looked at the null space for this matrix in the last video. And there are some important connections if you've had linear algebra that you might remember about the dimension of the null space and the dimension of the column space. You might remember that the null space for this one was 0-dimensional. Our column space here is 2-dimensional, all of R2, that is 2-dimensional. So when I think about finding a basis for this column space, I need to find a basis that contains 2 vectors. All of R2 is 2-dimensional. 2-dimensional. Right, all of the xy plane, 2-dimensional. So when I find a basis, I need 2 linearly independent vectors that generate this whole space. So there are a couple of ways to think about that. You might start with these 2 vectors we started with, and in the definition here, these 2 vectors, 2, 5, and 4, -1, are pretty clearly linearly independent. Remember, it's pretty easy to check if you have only 2 vectors, whether they are linearly independent or not. They're not scalar multiples of each other, so they are linearly independent. If you have more than 2, you can't use that shortcut. But for 2, that's nice. So these are pretty clearly linearly independent, and they are in R2. And we actually thought about this set of linear combinations of them giving all of R2 by really using the fact that one of them kind of gives motion in one direction and the other one covers the other direction. So one possible basis for this null space is really just these 2 vectors. And if I'm really focused on thinking about the column space of this matrix this way, maybe that's what I write down for my basis for this column space, just those two vectors, 2, 5, and 4, -1. I might also think about writing a basis for this column space by noticing that the column space is really all of R2, and we have a standard basis for R2 that's maybe a little simpler to work with sometimes. So the standard basis for R2 really would just be the two linearly independent vectors that are unit vectors and along the x-axis and the y-axis. So the I and j vectors, we sometimes call them, right? So you could certainly use that. It might depend on what you're going to do next with this basis, which one you would prefer. I guess if I'm going to do a lot of computation with these basis vectors, I might prefer the second one because zeros and ones are a lot easier to compute with than these other numbers. But really, any two linearly independent vectors in R2 are going to generate all of R2. Any two linearly independent vectors in R2 would work for this one, since we're talking about all of R2. All right, so two-dimensional column space, two linearly independent vectors that generate that entire space. All right, let's do the same thing for this example here. We're going to think about describing this column space geometrically, and then the real purpose would be so that we can find a basis for this column space. All right, so I'm going to do the same thing here that I did over there to start with. Just do this scalar multiplication and vector addition. So I'm going to just write this down. 2a plus 3b plus 0, 4a plus 6b plus 0. And then in the third entry, I'll have 0 plus 0 plus c. Okay, so again, don't be distracted by the way things line up in the entries here. This is a 3x1 vector, right? I took a 3x1 vector and added it to another 3x1 vector and so on. I get a 3x1 vector, right? So this first entry is all of 2a plus 3b. And then the second entry is 4a plus 6b. So sometimes students have a little bit harder time thinking about the geometry of this. I'm going to go right to kind of thinking about an x, y, z coordinate system here and thinking about what we have here. So let's just think about x, y, z coordinate system. I'm going to start by thinking about the third entry here. So that's the only place c shows up in here. And c can be any real number. So if I think about this as a vector in R3, right, I have 3 entries. The question is it all of R3? I might notice that that third entry really can be anything. And is not really specifically related in any specific way to the other two entries in this matrix. So in terms of an XYZ coordinate system, we might think about that as in the z direction, essentially we're going to have everything all up and down in the z direction. You might notice I intentionally constructed this matrix so it was easy to see some relationships. Sometimes it's not as easy to see and you have to do a little bit of algebra. But you might notice here that what I have in the first entry, which when I think about drawing a vector in R3, just like here in R2, the first entry, you're usually going to sketch that parallel to the x-axis. And the second entry, you would sketch parallel to the y-axis. And so remembering a and b can be any real numbers, but whatever you get, so whatever you choose for a and b, -16 and 4 or whatever, whatever you get in this first entry, notice that whatever you get in the second entry is going to be twice that. So these two entries in my matrix have an important relationship. And again, I made this example so that's easy to see. If it's not so easy to see, maybe you do a little bit of algebra to figure out some relationships between those. But in this one, you might notice that the second entry, which we would sketch parallel to the y-axis, is 2 times the first entry. So y is equal to 2 times x, and z, or the third direction, can be anything. Okay, so since the z direction can be anything, I'm going to start by thinking about y equals 2x in the xy plane. All right, so y equals 2x in the xy plane. In the xy plane, that's a line, y equals 2x. Think about slope and be sure you pay careful attention to where your x and y axes are, right? Rise and run and all that stuff. So, okay, so that's just a sketch. I didn't scale anything off there, but sketch of the line y equals 2x in the xy plane. But then because in the z direction, the third entry, we can have anything, just thinking about that going all up and down parallel to the z-axis. If you think about that, connecting back to that stuff you did in Calc 3, multivariable calculus with three-dimensional stuff, right? Maybe you recognize really what this is geometrically is that this is the plane y equals 2x in R3. So it's not all vectors in R3, it's all vectors on the plane. Remember, the column space is really vectors, not the plane itself, but the vectors on the plane y equals 2x. Okay, so that helps in thinking about a basis, right? So remembering that when you think about a basis, so between this video and the prior video I did about null space, we've talked about vector spaces that are 0-dimensional, 1-dimensional, 2-dimensional, 3-dimensional. So we've talked about lots of different dimensions of vector spaces. So this one, if we think about a plane, in some ways is like this one. This is really a whole plane. It's the xy coordinate system, a plane. I really, again, need two linearly independent vectors to generate this whole plane. And there's a couple of different ways you can think about finding those two linearly independent vectors. Probably for this problem, either way, you maybe get the same thing. All right, I'm going to start by thinking about it geometrically, and I actually have done this specific plane in some other videos that we looked at. But thinking about forming a basis for this plane, one easy way to do that is thinking about the geometry that I need something that's going to generate this line, y equals 2x, right? So that line that I drew there is in the xy plane. So I might use, I'm kind of running out of space here, but, and I'm running out of ink. We'll get a different one. All right, so. All right, so thinking about that vector there, so that has to satisfy the relationship y is equal to 2x. So when x is 1, y is 2. And then I drew that when x is 1, y is 2. Make sure you write down the right numbers in the right spot. And then when I think about how I drew that was in the xy plane, so the z entry, third entry, is 0 there. So that generates everything along that line. And then I need another vector to generate everything in the z direction. So there's lots of vectors you could use. Maybe the easiest one is just kind of how I drew this, just going up the z-axis. So the vector 0, 0, 1. All right, so I used geometry to think about that. And again, remembering that a plane is two-dimensional. A plane is two-dimensional. This plane lives in R3, right? We're in an XYZ coordinate system, but it's not all of R3. The plane itself is two-dimensional. This plane is just the XY plane, right? So the whole plane. So graphically, they maybe look a little bit different. They maybe live in a different overlying vector space, but this plane is two-dimensional, so I have two linearly independent vectors used to generate a basis for that plane. So I thought about that geometrically. You can also think about it algebraically. If you go back up to the original definition of column space, what I want is the vectors that are used to generate all of these linear combinations. And you can see that you're not going to get entries in that the third spot in this linear combination unless you have something that's non-zero in that third entry. So 0, 0, 1 happened to already be a vector in my matrix that I started with. That was used to generate what we had here. And then you might also notice that although in using the definition, I wrote this down, that really there's some redundancy here. That because 2, 4, and 3, 6 are scalar multiples of each other, 2, 4, 0, and 3, 6, 0 are scalar multiples of each other, I don't really need both of them to generate all the linear combinations that I would get from just using one of them. So I could use 240, or I could use 360. I don't need both. I could also just use any non-zero scalar multiple of either of those, like 120 maybe would be a simpler version of a scalar multiple of that. So this is one possible basis. Really, any two linearly independent vectors that are on this plane would also work. You want to make sure they satisfy these relationships, right? That y is equal to 2x. So you need to make sure they're on the plane and that they're linearly independent, so not scalar multiples of each other. But any two linearly independent vectors on this plane would work. You can get here by thinking about it geometrically. You can get here by thinking about it algebraically. Ideally, you can think about it both ways and arrive at the same place. The more ways you have to think about something, the more flexible your understanding is, and the better you're able to apply that in different situations where maybe one thing is more complicated, right? Maybe the algebra is more complicated in a problem you're looking at, but the geometry is easy. So you ideally want to be able to kind of arrive at the same result sort of either way, algebraically or geometrically. All right, do some work with column space and be sure that you're also getting to that point about thinking about finding basis for column space, and make sure you try all that homework.